So the way in which one would do test of GR, especially UC. So I'm going to restrict only to compact binary mergers, and this test especially is something which is very which is originated from the way of dealing with the binary compact binary dynamics in the perturbative regime, that is the in spiral, or early in spiral if you like to say. And the early in spiral is something which is well described by the so-called post-Newtonian approximation. So what is shown here for the for those who are not in the field is the gravitational waveform. That is what is shown as the chirp signal. As the signal chirps up, you can see the increasing frequency and amplitude as the system evolves. And what is shown on the top is the two black holes. And you can see that early on the black holes were wide apart, and as the dynamics progresses, because they lose energy, angular momentum, and so on, they come closer and closer. Then they eventually form a single object, that is the merger. And then, of course, this new remnant object has got a lot of asymmetries, which is radiated away in the form of ring down. So that is the last part of the remnant black hole. So mostly this test will focus on the adiabatic in spiral regime, where not just GR, many other theories of gravity also have got unique predictions about how the waveforms in these series could be. These results from alternative theories are not very, not in as much rigor as in GR, but still there are many interesting physics which different theories could propose. And these are the kind of tests that we could be using data to subject to doing this test of GR. Now, of course, we are in the adiabatic regime where the omega dot due to the in spiral by omega square is much less than 1, and this is the basic paradigm. And just to give you a complete picture, so what is shown in the early thing is the in spiral, and later on when they come very close to each other, your the post-Newtonian treatment, which really relies on a slow motion weak field approximation of the dynamics, is no longer valid. So you have to use essentially numerical relativity simulations to solve Einstein's equation numerically. And eventually, once the remnant black hole is formed, it gives you the quasi-normal mode ringing. That again is a regime where things can be, you can apply perturbation methods to do that. So both in the early in spiral and the late ring down are the two domains where you can apply analytical techniques. And especially this method relies rather strongly on the analytical treatment in the domain of adiabatic approximation, where one can compute waveforms and looks into how the dynamics of the binary as described by an alternative theory of gravity could deviate from GR. Okay, so that's just a quick thing about the binary black hole or compact binary dynamics. So just to give you an idea about the thing, so what usually post-Newtonian approximation would do is to essentially use energy balance. So in the energy balance, you equate the loss of orbital energy of the binary to the flux observed at observed far away from the source. So these are two kind of independent quantities that are computed. That is allowed because the adiabatic approximation. The flux, especially in the post-Newtonian thing, is a post-Newtonian series, but also it is also multipole decomposed, because using the different types of multipoles helps you deal with the non-linearities of the Einstein's equation in a very efficient way. So one uses, for example, UL and VL with multi-index U's and V's are the mass type and current type radiative multipoles. So these are the ones which are observed at infinity. And you can see that 1 by C square, 1 by C4, this the ongoing expansion is a practical expansion V by C. So that is a post-Newtonian series. And the leading term, for example, 1 by 5, the Uij1 would correspond to the Newtonian or 0pn term in the expansion. And as you go, this will go in increasing complexity, 1pn, 2pn, etc. And this one and this one with the bracket, that denotes the time derivative at this one's time derivative with the obvious multiple moment. Now the epsilon is the orbital energy of the system, which again by in the Hamiltonian formalism or Lagrangian formalism, we can get the conserved energy. That's what it is. So you see an expansion in x. So x is basically related to the orbital period, orbital frequency, which in turn is nothing but the V by C square. So it's related to V square. So this is an expansion again in V square. And this is, these two are used. So basically you compute flux using the equation that is here, and use energy, the orbital energy obtained here, and use them to compute the phasing formula by invoking the energy balance. So that is the basic idea or basic approach towards constructing the phasing formula. Of course, the computations of these quantities, especially the flux at high orders, is extremely complicated. That is why it has taken 2 or 3 decades since its inception to reach the level where it is currently. Okay. Okay. Now, so after doing all these things, what you really want is a frequency domain, time domain and frequency domain. It shouldn't matter. The waveform, gravitational waveform for h of t, and here I've taken a Fourier transform of that. So s tilde of f corresponds to the frequency domain gravitational waveform, which has got an amplitude which is a of f, and a e raised to I phi of f, where phi of f is the frequency domain gravitational wave phasing. And of course, frequency domain is much more natural and much more natural to use because of the match filtering technique that we employ to detect and do the parameter estimation. So match filtering is a technique where we use the best use of our understanding of the waveform to look for, that is to detect, as well as to do the parameter estimation of the signals that are there in the data. So hence I'll be talking mostly about the frequency domain waveform or the phasing, but you can equivalently do all these things in time domain, though things and approaches will be slightly different. So now what is shown here in the phi of f expression is the structure of the post-Newtonian phasing formula in the frequency domain. And so we can see that there is an expansion V. I've set C to 1. And so this is a series in V, Vk, as you can see. And there's phi k, Vk, basically where phi k's are the post-Newtonian terms at different post-Newtonian orders. And interestingly, the post-Newtonian series also has got logarithmic terms at certain orders. So for example, there is one at 2.5 pn and one at 3 pn and so on. So the first one is the 2.5 pn. It's not as frequent as the other one, because all the other ones starting at V0, the Newtonian order, you can get at different orders, but there are only 2 logarithmic terms until 3.5 pn in the phasing. That is 3.5 pn would mean V by C raised to 7. That is the convention. So basically there are phi k's and phi kls which sort of characterize the phasing structure. And this phi k's and phi kls will be a function of the source parameters essentially. So that will be a function of the 2 masses and 2 spins. And if you're in a neutron star system, it may also depend upon the tidal thing, etc., etc. And maybe eccentricity if you are in an eccentric. Okay, I'm not following the chat messages. Are they?
No, Arun, there are no questions. You can.
Okay. So if there is anything, please, somebody should stop me and tell me. I'm not following. Yeah. So that is what it is. So you got, so basically the phi k and phi kls, which characterize the post-Newtonian phasing, are functions of the source parameters. Right. Now this post-Newtonian coefficients, because you are going in the increasing order of the post-Newtonian accuracy, you will encounter more and more nonlinear interaction, because basically what you're doing is to approach the solution of Einstein's equation in a perturbative way. So you will see, as you go to higher and higher orders, you will see more and more mixtures of various nonlinear interactions which will come into picture, and which will have to be accounted for in order to get the gravitational waveform. So as you go higher and higher in the post-Newtonian orders, you will start seeing the effects of many nonlinear effects.
Hello.
Yeah.
Yeah. So what are these phi k's? Can you tell it specifically? Because I can see in the expression of phi as a function of f, of frequency. I think what are these phi k's? These post-Newtonian terms which you have just mentioned.
Yeah, so this will be simply functions of, so I'm saying this is going to be some polynomial in eta. So so if you take, so you can take the phi 0 here, that is 1, that is how it is normalized. So you will see that phi 0 basically is what is normalized out. So the term is going to have some structure like this, where the V5 is factored out, and eta is out. And the 5 Ks are going to be essentially, if you are thinking about non-spinning systems, 5 Ks are going to be polynomials in eta, for example, something times eta plus something, or some a plus b eta plus c eta square and so on.
Okay.
And if you are in a spinning system, you will also have chi1, chi2 and various things coming in.
Okay. Thank you.
Is that clear?
Yeah.
Yeah, sure.
Thank you.
Okay, fine. So I think the important thing to keep in mind is as you go to higher and higher orders, you will start seeing various types of nonlinear and the physical effects in the phasing formula. Okay, so this is just to give you an overview of the various arrays, because this is a very important thing, because the essence of this test really relies on the diverse physics that the post-Newtonian phasing coefficients.
काली मोर सब जगह स्टाफ आइतले टाइम टेबल स्टाफ सब जगह लगे दिले.
Yeah, okay, so then so this is like a quick summary of various nonlinear or various effects in the system. So at the 0 PN, of course, you are looking into quadrupolar gravitational wave radiation, and one of the interesting things that comes from the Newtonian order phasing term is the chirp mass. So chirp mass is a combination of the component masses, which is unique, and that is what is the most determined of all the mass parameters. At 1 PN, you got another set of terms, functions of M1 and M2, and that allows you to actually estimate both the masses, because earlier you could only measure a combination of the two masses, but 1 PN coefficient will also allow you to separate these masses or independently measure these masses. And if you're on an eccentric system, for example, you will also start seeing the effect of Periston advance. So that is the well-known advance of Periston that we see. So it is that happens at 1 PN order. And if you go to 1.5 PN order, you start seeing what is called the tails of gravitational waves. So I will explain briefly in the next slide. So this is one of the unique nonlinear interaction which happens in the gravitational wave waveform in GR. And in addition, at 1.5 PN, you also start seeing spin effects. So for example, at 1.5 PN, you will start seeing the effect of the S1 and S2, the component spins, if they are spinning. They will be interacting with the orbital angular momentum. So S1.L and S2.L kind of terms will start showing up in the phasing formula at 1.5 PN. And so if you go to 2 PN, so 2 PN, you start seeing the spin interaction. For example, S1.S2 or even S1.S1, the self-spin term, for example, we'll start seeing at second post-Newtonian order. And that also means that you are also sensitive for the first time to the spin-induced quadruple moment. For example, you've got two stars, maybe two stars, which may not be black hole. And when these objects rotate, it leads to a deformation of the object. And due to this deformation, there is a quadruple moment, and that is like a spin-induced quadruple moment. And this spin-induced quadruple moment starts appearing at 2 PN order. And this is a very good way to look for the nature of the object. For example, this will be different for a black hole and a neutron star. For example, if you could measure this quantity very well, you could actually be using it to distinguish a neutron star from a black hole, for instance. So again, 2.5 PN, you have this tidal heating term, which is what Sukant's talk is about, especially with spinning. So in the case of spinning thing, you will be having the tidal heating term, which is actually a very important term which characterizes the presence or absence of the horizon of the black hole, if there's a black hole. All right. And then, of course, 3 PN, you've got even tails of tails, which is again a higher order interaction of the tails with tails. And the tail square, because you are computing the flux, and there are many of the things are quadratic, so you'll get tail square term. This again a very unique type of nonlinear interaction term that is present. At 3.5 PN, I told you at 2 PN you got spin-induced quadrupole. At 3.5 PN starts capturing the cubic interaction of spin. So you have got S1 square dot S2 or S1 cube and so on and so forth. So so at 3.5 PN you can start seeing spin-induced octupole moment of the component objects to appear in the gravitational waveform. And at 4 PN, for example, will be the tidal heating equivalent term if the system is non-spinning. So because the horizon structure is different for a spinning and a non-spinning black hole. So if it's a non-spinning black hole, the tidal heating term will be coming at 4 PN order. And if you go higher at 5 PN, you start seeing the finite size effects. That is, if you are seeing a merge of two neutron stars, you will start seeing tidal interactions between the neutron stars. So these kind of effects will start appearing at 5p order. So this can go on. Now we can see there are many. There can be tails of spins and then tails of spins and so on. So as you go to higher and higher order, you start seeing many of these effects. So basically, by measuring these post-Newtonian terms, you're actually having access to these very different and diverse nonlinear or physical effects that are happening in the system, and that is why we can by observing them or by estimating them, you are just setting all these effects to test. Okay, with that, I think we can come to the basic philosophy. So what I said, it is expected that one or more of these effects could be different, either qualitatively, I mean, in terms of the structure itself, or quantitatively in terms of the details of the interaction in any non-GR theory. So that is expected.
Arun?
Yeah.
Sudipto here. So there is one short question I have.
Yeah.
So when one do this PN expansion,
yeah,
is there an assumption that metric is the only field, or you can allow other tensors or scalar field also?
Yeah, so in the GR approximation, of course, you got only Gij, but in other theories where there are scalar tensor theory, for example, even there you can also invoke a post-Newtonian expansion, get the equivalent term. So it can be done. So the one which I will talk about, we'll be talking only about the metric, but in other theories also where there are external extra fields, you can still do a post-Newtonian expansion, which will come with additional conditions, I suppose, on the, on the overall formalism.
Is it expected that then it will modify even the zeroth order result, or?
No. So I think I'll come to that. So I think, so usually one of the unique predictions of the scalar tensor theory, if you think about that as a something like a Brandstede theory, is that it will start giving you dipole radiation.
Okay.
So I think I'll come to some of them, and I think yeah. So I think I will be coming to some of these effects later. We can talk again about that. So it may modify, it may not modify, depending upon what kind of fields you are invoking and what are the details of these fields. But what it will change and what it will not change will depend upon really on the kind of fields you are considering, what kind of interactions you are invoking, and so on. Okay, fine. So I think, as I said, we are really looking into the physical effects, which could be different in the modified theories. And the hope is that by precisely measuring these post-Newtonian coefficients, you can carry out, you can ask the question that how consistent is this coefficient with the prediction of GR? And if there is an inconsistency, it could be due to a breakdown of the GR. That is the hope, right? So of course, if you look into other kind of tests of GR, it is in very much similar in spirit to, for example, the PPN formalism, and that is done in the 70s by Clifford Will and other collaborators, which was used for solar system based tests. For example, they talked about the constraints on deviations of the metric of the sun in some sense, using various types of probes. And similarly, in the binary pulsar test, you invoke what is called the PPK formalism, the post-Keplerian one, where you look into the various orbital effects which come in the binary pulsar system and how different they are from the predictions of GR. So this is exactly the same spirit, just that we are now using the post-Newtonian phasing formula and invoking or introducing deviations, which is what is being set to test. So to summarize, this is like a theory agnostic test because we are using the best use of our knowledge of the dynamics in GR, and we are looking for deviations about that, because what we know the best we use to the maximum, and hence it is in principle agnostic to test. Of course, if you have a theory of gravity where we know how precisely these coefficients are modified, and if you know what are the new free parameters which will enter, of course you can again infer those those parameters as well. So that could be like an extension of this, or you can use these bounds to map it onto those kind of alternative theories. Anyway, I'll come to some of them.
There is one question.
Yeah.
So, the question is how these different post-Newtonian terms are obtained from Lagrangian densities of different gravitational theories.
Yeah, I mean, I think that will depend upon, you're saying how are the modifications to GR in terms of additional fields and so on addressed in the treatment. Is that what you're asking?
Yes. I mean, how, so these different Pn terms and different Lagrangian densities, how are these two related?
Yeah, I mean, I had to admit, I not worked too much on the theoretical front, but I think in the later talks, for example, Enrico's talk and so on, may address them in more detail. But I'm not familiar enough to answer your question to a satisfactory level.
Okay, sure, thanks.
Okay, so if you think historically about the origin of this kind of test, this was really like the first first instance of this kind of test was done by Blanchet and Satyaprakash in '95. So this is this is like the measurement of the tail effect. So I mentioned about tail effect. So tail effects are essentially when you have gravitational wave going by, the gravitational waves may be scattered by the background space-time itself. So this scattering or the backscattering of the gravitational wave by the background space-time is what characterizes the tail. So it's going to be m cross qij kind of. M is a mass, the area mass, and m cross qij. Second time derivative will be the gravitational wave. And this kind of interaction is what captured by the tails. And when this was first computed, Blanchet and Satyaprakash looked into asked the question that how well can this effect be measured from the gravitational wave phasing formula, and how it could be used as a kind of unique test of GR. So basically, you ask how the tail effect as measured by the observation, how closely it matches with the predictions of GR, and then that is like a test of GR. So that is where this thing originated, and then it went on to taking different routes. For example, some of us addressed this question about how precisely can we measure the phasing coefficients at different orders, extending what was done by Blanchet and Satyaprakash. And so there the idea was to really measure the xi k or the phi k, what I mentioned, how much is delta phi k, and that accuracy will give us an idea about how closely it matches with GR. And then of course it was extended by Nico Younes and his collaborators. And they extended, in a more general framework. They introduced, our framework was somewhat basic. We only looked into the phasing formula, whereas they introduced amplitudes also, and also they went beyond the inspiral because some of the inspiral merger, ring down analytical waveforms were available, phenomenological waveforms were available. So they took it to the next level and wrote down a more general deviation, and that's often referred to as PPE formalism. And in addition to that, many of the following work, they really did an extensive mapping of several non-alternative theories of gravity, and they could map it onto the PPE or PPE phasing or amplitudes and so on. And beyond that, they also asked the question that what are the existing constraints on these parameters from other observations such as binary pulsar and so on. So the entire paradigm was taken to the next level by the work of these people, and that is one stream of things which is still continuing. I see more and more work coming from them. And another approach which was taken by, for example, Johnny Lee, Agathos, and Chris Vandenbroek, and so on, were to develop algorithm, on the real to be applied on real data. And then they argued that the best way to carry out such tests is the null test of GR. So there is to really add free parameters on top of the phasing formula and then measure them and ask how consistent that is with GR. So that is like a null test. I'll come to that in the next slide. And this framework, which of course it was not just the formulation, they did an algorithm. So they developed an algorithm to carry out this test, and this is the structure called Tiger that is used now by the LVC to derive all the bounds using gravitational wave data. So these are, this is like a short summary of how things have evolved in the past decade or more on various approaches to this test. Okay, so now what do we mean by a null test, right? So I told you that you can have a phi A, that is the kind of phi k that I use. So if it is a modified theory of gravity, you would expect phi A to be phi A GR into some 1 plus some delta phi A by delta G. I can get a dimensionless quantity, which I will call as some delta phi cap. So by construction, delta phi cap GR is 0 because there is no deviation. But you would expect that in an alternative theory of gravity at one or more post-Newtonian orders, you would expect to see deviation, that is delta phi A will not be equal to 0. So what you do on the using the data is to get the posterior distribution on delta phi A hat, let's say like this one, this is like a toy thing. So you get a posterior distribution, and if GR is correct, you expect it to peak at 0, and it will have a width, and this width in that case is what is given by the observation, and this will give you upper limit on the value of that particular delta phi A hat, so which should be 0, and the lower the upper limit, the better are the bounds. Of course, depending upon the situation, you will derive it at various fixed confidence levels, and that is usually the LIGO follows the 90 percentile one, but it's up to depending upon the situation, it could vary. So now just coming back to the interpretation, what are the possible outcomes of the thing, right? So it can happen that you see a statistically significant offset of the null parameters, the delta phi A hat, and this could signify a possible deviation from GR. And of course, this has to be, before you claim a deviation from GR, you have to really rule out all kinds of waveform systematics, because if the waveform that you employed to do the data analysis was not capturing some of the physical effects or some of the details of the waveform and so on, you could get these deviations as an artifact of this systematics. And one should be the important thing for the whole of this thing is to make sure that the systematics, waveform systematics, are under control. That is a very, very important condition. But subject to that, if you are sure that a waveform systematic cannot account for such a large statistical deviation, then of course one may be in a domain where we are looking into a possible deviation from GR. Now the other kind of situation which is more likely with our sensitivity is that the measurement is consistent with 0, like I showed you in the previous slide. Then the associated width of the distribution could be used to derive limits on the deviation on that post-Newtonian coefficient. So I will be getting some upper limits on all of these post-Newtonian terms, or the post-Newtonian, the phi A hats, delta phi A hats. And this, of course, can be used in principle to rule certain theories out. If I have a prediction from a theory which is inconsistent with the bound I derived, I can say that that theory is ruled out. Of course, we are not still in that kind of regime unless for very exotic ones, I think. So, but so in principle, the deviations, the bounds on the deviation parameters can be used to rule out theories. So I'll come to some of the subtleties in future when we are in a more sensitive regime in terms of detectors. This is something which has to be carried out with extreme care, and I will explain it in the next few slides. But these are the outcomes, that if you see a deviation and you're sure it's not due to the waveform systematics, it is a way of looking for, so we have seen a deviation of unknown nature, because this test will not tell you anything more about that. We only know that we have seen a deviation, that's it, right? So in some sense, that is a drawback because we don't know anything about the theory. But in other sense, it is an advantage because we are able to carry out searches for beyond GR and beyond GR effects in a very in agnostic manner.
Arun, can I ask one question?
Sure. Yeah.
So in all this analysis, the waveform model that you consider, that is built using GR, right? I mean,
correct. Yeah.
So, I mean, is it not, I mean, natural to expect that they should match with GR, I mean, even if there are deviations, because the waveforms have been constructed assuming GR. So is there bias in some sense? That's what I'm...
No. So I think we can do. So there are two types of deviations inherent, right? There are one types of deviation could occur in such a way that the deviations can be easily absorbed into redefinition of the GR parameters. For example, it may appear the deviation may be there in the data or in the signal, but the deviation may be simply absorbed into redefinition of mass, for example. right? So those kind of deviations cannot be like you guess. We cannot detect them. But the other type of deviation is something which goes beyond that. And there, of course, we are introduced free parameters, and we are, of course, we have got a higher dimensional parameter space, but we will be able to see or obtain bounds on them. So on certain classes we cannot, but just because we are using GR waveforms, there is no limitation because we are introducing free parameters and we are setting limits on them. Hence, in principle, there is no limitation unless these free parameters happen to be in such a way that they can be absorbed into one or more of the parameters completely, of the masses or spins completely.
Okay, okay. Thank you. Thank you.
Okay, fine. So now we entered this tricky regime that how do you carry out this test? We have, I told you there are different, until 3.5 p.m. we have got around 8 free parameters, 8 post-Newtonian orders for which we know what GR is predicting. And the ideal thing to do would be to simultaneously fit or simultaneously estimate all 8 of them from the data. So this will be referred to as multi-parameter because you are simultaneously estimating multi-dimensional or multi-parameter deviation from GR. Or it may not be all 8, maybe 6, for example, but it's a batch or a multi-parameter test. And such tests are more tuned to the feeling that an underlying theory of gravity, if it's different from GR, it might modify more than one of the PN parameters. So it is not, it's more natural thing to do. Now, doing such a test is too demanding. So that is because we have a GR parameter. So I have shown you that the space. So the theta GR here refers to all the GR parameters that are required to describe the signal. And then you've got the deformation parameter. So together, if you look into a non-precessing but spinning binary system, you have around 7 GR parameters, including masses, spins, etc., and 8 of the non-GR one. For example, you will be looking into 15-dimensional space of parameters. And understandably, this is a very strongly correlated space because there'll be a lot of correlation between the non-GR ones and the GR ones, and also in between the non-GR ones. So this is a very, very demanding test, and it's not easy to carry them out. So basically, simultaneous measurement of all PN coefficients is, of course, a very rigorous test, but it is too daunting for the present generation detectors. I will also show you it is daunting also for the future detectors towards the end of my talk. So one compromise you can do is that instead of looking for a 8 parameter deviation of GR, you look into 8 1 parameter deviation. So that is like breaking into tests. So you, at a time, in addition to the GR parameter, you are measuring only 1 of the 8 of them, right? Then you keep changing this one. So you're looking into different types of.
Hello.
Yeah, hi.
You just mentioned that these parameters are strongly correlated. Now, I think you are making it too much compromise. 8 parameter test, 8 single parameter, that means you're assuming the other parameters to be fixed or held constant. Now, once you do that, you are losing for the probability or the uncertainty on the other parameters for the simultaneous measurement. Now, I think isn't that too much of compromise to consider 8 1 parameter test or taking 1 parameter single time?
Yeah, so you're saying that instead of doing 8 parameter test, into doing 1 parameter test is a compromise. It's a severe compromise.
No, I'm saying this severe. This can work well if they are loosely correlated. But since they're strongly correlated, now if you take the complete set of the matrix, or if you construct a Fisher matrix, say, and then you have the correlation of the parameters in the Fisher matrix, and you are leaving out all the correlation, then the value that you will get for the marginalized value of one parameter and the conditional value that you have just mentioned, there will be largely different because there is a strong correlation exists.
Yeah, correct. So I think that is the whole point. So I'm saying, so that is really the point I want to stress in this talk. So the point is that if you are considering this as a null test of GR, where you are interested in detecting a possible deviation from GR, it may be, so each one of these 8 tests is a deviation from GR. I mean, it can characterize a deviation from GR. But if you want to, like you have on the back of the mind, if you want to map these constraints to a physically meaningful space of alternative theories of gravity, then this eight one parameter test is going to give you artificially stringent bounds.
Okay.
But they're still, as a null test of GR, they are indeed meaningful. And systematically varying them, it is a way of also tracking and if you detect something, it is a way of tracking how these things are modified. But I agree with you that this, the one parameter test has got severe limitation in mapping it back to something. So if I see something at a particular post-Newtonian order to be different from GR, it doesn't mean that the alternative theory of gravity modifies something at that order. It could be that it is modifying something at a higher order, just that I am detecting due to the correlations, I'm seeing it at a lower order. That's the point you're stressing, right?
Yes.
Exactly. So that is true. But I think we are doing it only, and our first aim is to detect a deviation. And in that spirit, if you are looking for if you're looking at one parameter deformation of the GR, this is a well-posed one, and that's what we are doing.
Thank you.
So I'll come back to the 8-parameter one and how we overcome that, because it's you can imagine that all 8 of them are it's a strongly correlated parameter space. That is the big challenge, and how do you break that strong correlation is the challenge, which I will come to towards
possibly a combination of the 8 parameters which will be degenerate, which will not be a non-degenerate state. You can build out of that, taking the eigenvalues of it. Right?
Yeah, correct. Exactly. So I'll come to that. So that's what we do. So I'll come to that. Yeah, thanks for the. Okay. Okay. So let's now look into the what we have from the results of results so far. Right, so what is shown on the right side is really the 150914, the first binary black hole detection, and the bounds that we derived at on the various PN coefficients on that, and that's compared against the binary pulsar test. That's the relativistic pulsar is the blue one, just to compare that. Now, so what I stressed, like you stressed, the important point is that multi-parameter test is now broken up into 8 pieces or 8 independent tests. That is what the result are. And one should be extremely cautious when one maps this onto the alternate theories of gravity, because for the reason I explained, from an effective, from a kind of effective field theoretic point of view, for example, if you are having a deviation from GR that happens at a very relativistic regime, you expect that the modifications to the post-Newtonian structure might start appearing at a particular order. So it may happen at 2pn, and everything above that may be changing. So such things, such things have to be taken into account before you map. So that is something to be done. So there is no unique mapping of these bounds onto the PN coefficients in modified theories of gravity. And if one is doing that mapping, there are implicit kind of assumptions which one should be aware of. And that is what we can do. That one can do that, but it should be clear that there are many implicit assumptions which has gone into those bounds. Yeah, I think that's so. You can see this is the first bound that we obtained. And now there's another thing which was what Sudipta was asking, that some theories of gravity, especially the one where there are extra scalar fields, can predict dipolar gravitational waves. So we know that in GR the leading order gravitational wave is starts at the quadrupolar order. And but there can be theories due to additional fields, it can come as dipole. But the advantage with dipole, even if you don't know the theory, is that based on pure dimensional multipole arguments, you can say that your dipole flux will go as di double dot, where di is a dipole moment, and that would mean that your xi or the phasing dipole modification to the phasing will be proportional to 1 by v cube. So I told you that the overall phasing of the Newtonian order was 1 by v5 in my phasing formula. So here is 1 by v cube. So that is like an effective 1pn term. So regardless of the theory that you're dealing with, that is approach here, any theory of gravity that predicts dipolar gravitational wave will give you some minus 1pn term in the phasing formula, which is identically 0 in GR. There is no such term in GR, and any bound on that term is going to be of extreme importance in ruling out such theories or such fields which can mediate these theories and the coupling, etc., etc. So what I've shown you is are the expected bounds that we computed. So alpha is a parameter that introduced into the amplitude of the waveform, and phase is characterized by the beta, and this is just showing the expected constraints on the amplitude and on the phase parameters with future detectors. That is like the, what we can expect to learn in the future was the thing. So you can see that amplitude, of course, is not so accurately estimated, but phase is what we are more sensitive to, and we can go to extremely good bounds on on the phasing deformation with detectors. Of course, you'll see that I have taken masses up to 150, 200 solar mass and so on, which of course are black holes ideally. And if you're familiar with alternative theories of gravity, you would know that many of the scalar tensor theories, like Brand's decay theory and so on, would predict zero dipole radiation for binary black holes. So the dipole radiation in is zero for binary black hole systems, and you require either binary neutron star or neutron star black hole. So something with matter to give you dipole radiation in that. But of course, there are many theories as can be seen. Maybe Enrico's talk tomorrow will also focus on some of them, which also, by invoking certain way of how the scalar field is interacting with the rest of the sector, you can even get binary black holes to give you dipole radiation. And that is the reason why one of such bounds, even for a binary black hole like system that LIGO keeps detecting, such bounds may be of interest to rule things out for such systems. So the basic thing is that the dipole radiation will give you a minus effective 1pn term, and which we have very good sensitivity to, because this is like a lower end of it's like the first pn order if you invoke it, and that is the most sensitive one. And our bounds on the dipole ones are extremely good, but one should keep in mind that there are, it's only a subclass of alternative theories which will predict such emissions for binary black holes. And even then, it's interesting bound to derive and set limits on them. Okay, so this is a this is like a snapshot of the existing results what we have got. So this is from combining all the events, not all the events, at least a few events which are appropriate for this test. Yeah.
If I request, if you can go back to your previous slide. So yeah. So this beta is what? This is a dimensionless parameter, or what exactly it is?
Yeah, I think I did not. So you can make it dimensionless. I did not show the equation. I just meant that it's a dimensionless quantity that appears in the minus 1pn thing in the phasing formula.
So GR limit will be beta goes to 0, or
exactly. That will be beta go to 0.
Okay. So therefore the constraint is giving a 10 to the power minus 6, right?
I think this is expected from the ET is a third generation one. So I'll show you, this slide shows you this bound. So this slide will show you the existing, the one from the first two observing runs is of the order of 10 to minus 3.
What I'm wondering is that, so this does not look to be a very stringent constraint, because we already have very stringent constraint from, say, Newton's law experiments.
Yeah, and also this is very well constrained, maybe also from binary neutron star observation, binary pulsar observation. So we are not claiming it is anything more stringent, but you have to keep in mind we are looking into the merger of two black holes, and if there are mechanism which turns on dipole radiation towards the late stages and so on, that is something which other experiments will not have access to.
Okay, I understand.
So this is a different regime is what is kind of important. I think I'll show you later also some plots by other groups where they compare with the binary pulsar test, and you will see that even the binary pulsar constraints on dipole radiation is much more stronger than what gravitational waves can put.
Okay.
Okay, so this is the state of the art in some sense, bounds from the O1 and O2, and the paper from O3 is being written, so it will be out in a month's time or something, So this, of course, the top one is just showing you a posterior distribution, what's called a Biden plot, and the number is shown in this figure at the bottom of the thing, right? So you can see that as expected. So okay, you'll observe that there are like 4 sectors in the thing. If you look into the y-axis, the dipole radiation is the most accurate estimated bound, and the next one is phi naught. So phi naught is mostly chirp mass. that is the next one, and chirp dominates everything. So that is why this is the most accurately determined one. And the next one, 5.1, 5.2, 5.3 are the next kind of sector or the class of PN coefficients, which that gives you a reasonable bound, which ranges from say like -4 to 4. And then in the higher order one, starting from 2pn, is not that well estimated. You can see that the range it is between -6 and 6 is the range of the box. So there are like different sectors, and depending upon our sensitivity. So this is just a reflection of what we can do with our existing sensitivity. And if you look into this plot, like I said, the -1pn bound is of the order of 10 to -3, and we can see that we are used only 5 or 6 of them because we are invoking. So we need systems where there is a reasonably long inspiral, because that's what we are actually testing, and that is why we restrict the analysis to only those where we are seeing a very clear cut and usable inspiral content. And there are two types of waveforms that were used. And that is just exactly, I mentioned that we have to make sure that our waveform systematics are under control. So this SUVNR V4 is effective one body based waveform, which is non-precessing. So they assume spins which are aligned or anti-aligned with respect to the orbital angular momentum. And the IMR phenom PV2 is something which will that is actually precessing, and it is like they capture the essence of numerical relativity in a way. So these are like complementary approaches to waveform. We use both and carry out the analysis to make sure that we are, if we see any deviation, it is not due to something which we are overlooking in the thing. And as we see more and more systems in the future with diverse physics, it's controlling the waveform systematics is going to be a big challenge, as you can imagine. Okay, and you can also see that on an average, you see that the bounds are weaker as you go to the higher PN order, though there are exceptions which has to be understood. So this is like a quick summary of where we stand with respect to these bounds now, and in the soon I think the O3 bounds should even be more improved. Okay, so just coming back now to focus on the limitations, right? So the single parameter test, as we argued or we found that the serious limitation is that it cannot be uniquely used to pinpoint a deviation at a particular PN order, and hence it's a null test but not easy to map. And so if you're using this thing to constrain specific alternative theories of gravity, one has to be excise caution. Of course, the multi-parameter test is what would help you overcome these shortcomings to a large extent. But of course, we saw that it's very hard to perform with the existing sensitivity. Okay, so like it was proposed, one solution to this problem is to optimize the null test in the sense that so there are 8 post-Newtonian terms, and they have different sensitivity too. I mean, at least the bounds have got different ranges. And what we can do is to ask the question from the point of view of a null test: can I come up with a new combination of these coefficients, a few combinations, which are the best measured linear combination of the deformation coefficient? So like it was mentioned, the simplest way is to diagonalize the matrix, get the eigenvalues and eigenvectors, and the eigenvectors will give you that linear combination which gives you the best estimated one. So what you do is that you had initially you got 2 sums, and the second sum of the deformation one you are now decomposing into a new, you're doing a rotation in the space, and you're getting a new linear combination where this d delta hat phi k are the new parameters. And of course, you would expect that depending upon how correlated, you may see that only 2 or 3 of them will be enough to capture most of the eigenvalues, and so that's fine because we just live with that. And that so in the sense, the bounds on these new coefficients are not on the individual ones. It is a bound on the overall post-Newtonian phasing structure. So that is the advantage, that we may still be doing a 2-parameter estimate or 1-parameter estimate, but now this number from this null test will give you overall constraint on the post-Newtonian phasing formula. So this is something which is ongoing, and with Sayantini Datta, Muhammad Salim, and so on. And I'll show you one of the preliminary results from here. So what we did is that, of course, with the existing sensitivity, we did not deform the Newtonian and the 1pn term. We just left as it is. We took a batch starting from 1.5 pn. There are 6 of them, 1.5 pn all the way up to 3.5 pn. Then we performed this analysis. So what is shown here are, so we again analyzed these events, the same events which I showed you in the 0102 paper. On the same events, we carried out this test and combined this information. And the combined information on the d phi 3 prime, for example, this is the new new eigenvector which corresponds to the entire deviation starting at 1.5 pn. And the new one is the obtained one, combining all these events is what is shown here. This is pretty much consistent with 0. And the second one is the second eigenvalue of that is what is shown by d phi 4 prime. That again is consistent. Yeah.
This 170104 is what convention of source? Because 14 is the 2014 source.
No. So 150914 would mean 2015 September 14th.
Correct. So what means the 170104?
Yeah. So that is something happened on the 4th of January 2017.
2017.
Yeah, 17 is the year.
First one is the year. Is that right?
Yeah.
Okay. Thank you.
Yeah, so I think these are interesting constraints, and the advantage, as I said, is that this is like optimization of the null test, in the sense it captures the entire structure. Of course, the obvious drawback is that though you obtained a very good bound, there is no way of mapping this bound to any alternative theories of gravity, because you've got a linear combination already. It's mixed up. And the number prefactors which multiply the different one will depend upon the masses and so on. So there is no way of mapping it back to the alternative theories of gravity. But still, from the spirit of the null test, this is a good way of optimizing the null test. And this is we have also shown. We also injected the mock non-GR signal to assess how well we can detect GR deviation, and that also seems to be giving encouraging results, though we are still in the process of looking into this and so on. So that this seems to be an intermediate fix where we can, in principle, have the spirit of the multi-parameter test by using something like a singular value decomposition.
Hi, Arun. Sorry. So in your previous slide, why is there a can you explain why is there a bimodality in delta phi 4 prime?
Yeah, so I think this is, I think it depends upon the operations we do, right? What we do is the following. So we will carry out multi-parameter usual parameter estimation runs, keeping all the 6 parameters free. And then we get the marginalized 6-dimensional posteriors from each one of them. Then we combine them for each one of the events. That's what we do. And the bimodalities are, because there are the way in which it combines, there are many, even if you look into the individual posteriors, which are I don't think it's clear from here. So yeah, I think if you look into this paper, the 0102 BBH paper, there are many systems which are showing shaky features due to the presence of noise or glitch and so on. So this bimodality, we believe, is a combination of that together with the, on top of it, we are doing the operation of doing diagonalization. So it's basically imprint of these noise artifacts being now coming into picture the way we do the SVD.
Okay, thank you. Thanks.
Yeah, there was one more question, I think.
Yeah, Arun, it's Suman.
Yeah.
So you discussed about the non-GR theories and how they can be tested using post-Newtonian. About non-black hole candidates for LIGO, do you have similar set of parameters or?
Yeah, I think I did not. I know that Vitor Cardoso's talk will be talking about it. So we can do multiple tests. For example, one using tidal deformability thing and one using the spin-induced quadruple moment. And so those results are going to be in the O3 paper, which we are writing. You will have those results. But if you want to look into the intermediate one, the paper which Krishnendu, Salim, and I wrote on the spin-induced quadrupole moment will give you some bound on this parameter and the bound on the black hole nature using that. Just like I think tidal heating, Sukant also had a paper. So I did not show it because I did not want to. I just wanted to be focused.
Okay. Okay. Thank you. Yes.
Okay, I think this is so. I think so. What the take-home message is that the singular value decomposition could give us some temporary respite if we really want to get a constraint on the overall post-Newtonian structure. Okay, now let us look into future. What all can be done, because we are going to have several more detectors. For example, this is a figure from Chamberlain and Eunice in 2017. So you can see that there's advanced LIGO, of course, that is this dotted black line. And then there is A+, which is like an upgrade of advanced LIGO. Then Voyager is like a 2.5 G detector. Then comes the third generation detectors, which are called Cosmic Explorer and Einstein Telescope. You can see that the sensitivity keeps on improving on the ground-based detector side. And then on the space-based detector side, you've got the LISA detector, that is this black curve. And I think what they considered are different types of LISA noise PSTs, because at that point of time, the LISA configuration was not frozen. So this is what the future is. So we are going to see, using LISA, we are going to detect mostly supermassive black holes which merge at the millihertz regime. And using the stellar mass using the Cosmic Explorer or Einstein Telescope, we are going to see the stellar mass binary black hole mergers like LIGO is seeing, but with much more sensitivity. And also we can go to very large masses if they exist, because the low frequency cutoff is much more smaller. It starts at 1 Hertz or 5 Hertz. So basically the future is going to be a 10-fold improvement on the ground-based detectors, which are with also a 10-fold improvement on the low frequency sensitivity, which is what is going to dictate how various quantities are going to improve. Okay, so let's go into the first result. So this is like a picture which I would have liked to explain if I had known, but I'm not an expert in this. But just to those who want to read more about it, this is a summary of various types of modification from various types of theories and their current bounds from various ways. So you can go back to this paper and read more about it. So the important thing to note here is that there is of course dipole radiation, which is like -1 PN, but there are other quantities which even go as large as -4 PN and so on. So these are like very low PN, effectively negative PN orders. And there are constraints, for example, large extra dimension and time varying G and so on. There are different theories of gravity. And of course, they have to be probed using different sources, which is what will give you the constraints. And they have also given you something on the higher side. So this just to give you an overview of the thing. We can come back to this, though I'm not an expert. But after I finish, if there are questions, we can come back to this. But let's look into the expected constraints. So this is a constraint that these people reported using future detectors. So left panel is a space-based detectors. I wanted to focus on what I like, but this contains the entire spectrum. And so you can see, if you look into the LISA thing, the EMRI refers to the extreme mass ratio in spirals, which are small black holes orbiting very supermassive black holes, this extreme mass ratio. And the IMRI would mean it's intermediate mass ratio, so mass ratio of the order of 100 or so. And IMBH would be intermediate mass black holes, like 500, 1000, etc. And SMBH would be in supermassive black holes, right? And of course, there can be also GW 150914 with advanced LIGO bound to compare this expected bounds from. So you can see that there is a lot of improvement. Of course, I think the plot Sudipta wanted is here. The dotted black line is actually the constraint from the relativistic double pulsar, and we can see that that beats everything else in the dipole regime. So I think there is no way of beating that in the low PN1, simply because it's in the low frequency evolution is what it is seeing, and hence it's much more sensitive. If you come to the right hand side, that talks about ground-based detectors with various things. I think they used with CET type detectors. They of course consider double neutron stars and intermediate mass black hole neutron star, blah blah blah, various types of sources. The spread or the shading is due to the fact that depending upon the mass and spin of these sources, these bounds can vary, and that is what is that is what captures the shady area. So you can again see that typically the bounds will is going to improve for most of them, and but of course in the low minus pn thing, it's going to even binary pulsar is going to be the dominant one, which is the most sensitive in terms of constraining those effects. Okay, so now that's about one parameter test. Okay, this is all about the single parameter test. But now let us look into the multi-parameter test. Now it sort of turns out that even if you use, so the orange curve is for Einstein telescope. Okay, I think it's Einstein telescope. Only Sayanthini would know, but I think it doesn't matter much. They're comparable, Einstein telescope or CE. For example, 200 solar mass and located 1 gigaparsec, the expected bounds are, so you can simultaneously bound 4 parameters of 200 solar mass, and that's all. If you go to 5 and 6 and so on, you won't be able to estimate. So the maximum number of parameters that you can simultaneously estimate in this using the 3G detectors, ground-based detectors, is 4. And if you look into the LISA case, we considered something like a 6.6 into 10 raised to 5 solar mass supermassive black hole at 1 gigaparsec, and that can actually measure things much better. That's fine, because that's about the larger SNR and longer observation time. And even then, you cannot go to above 5 parameters, in the sense if you go to 6 parameters and so on, the bounds become also a factor of 10, or the Fisher matrix starts becoming ill-conditioned, which is just a signature of the fact that things are breaking down. So even the multi-parameter, there is no way you are going to do the 8-parameter test, even using this kind of sources is what this plot would tell. Of course, there may be there can still be some golden binary which may have some of the features which may do this test, but that is, for the typical system, we don't expect even the advanced detectors to be able to carry out the multi-parameter test. And we know that the multi-parameter tests are important if you want to reliably rule out the alternative theories of gravity. So now that the basic message is that it is too demanding even for the future detectors. So that is this multi-parameter test. Okay, now comes the last part of the thing. So how do you overcome this, right? So one way of overcoming this is the process called multi-banding. So this is the following. So if you think about 150914, this is the first discovery, we saw them merging in the LIGO band. But the point is that if LISA was operational at the time when we detected it, or a few years before that, because the system would have stepped through the LISA band before reaching the LIGO band, and it can have a reasonable SNR of the order of 5, for example, in the LISA band, and we would have detected it. So in that sense, we may have seen the source. The plot shows also the time. So the time is the time till the last stable orbit, or the merger approximately, is 5 years, and then so you can see that 5 years is here, a few hours and seconds and so on. That's how the thing is shown. So I think we have shown two curves. First one is for the evolution of 150914, the gray one, at 400 megaparsec, and we also considered a 500 solar mass system. So this is how the amplitude of the source would evolve as a function of frequency over the time, and this is how it will merge. So this shows the merger and the ring down, because it just goes down. Right. So the important thing to keep in mind is that when the 3G detectors are operational with like 2030 plus, LISA is also going to be operational. LISA may also be simultaneously operating. So there is this interesting prospect that one may be able to see sources, the same source in both the bands, both CE, and if you go back to the LISA data, also in the LISA data. So you may be able to combine or observe the same source in multiple bands, one the low frequency band of LISA, and one the high frequency band of CE or ET, whatever that is, right? So combining these two information, so what it will do basically is that LISA is very sensitive. LISA is sensitive to the low frequency evolution of the system, and hence one would intuitively guess that the lower PN order terms or PN order coefficients it can estimate reasonably well, because that's where it spends most of the time. Now, CE will have very good sensitivity towards a merger, and the high relativistic, the high PN order terms, it will be very good sensitivity too. So if you combine them, if you combine the information from these two sources, you hope to gain more than just the individual one. So that is the whole idea about the multibanding. And I think this was first done by Ramya Nair long ago, where they discussed about combining this information from the point of view of test of GR. But this became a more very active field after the first discovery, starting from Salvatore Vitale, Alberto Cesana, and so on and so forth. There are many work. I did not cite it. That's the dot. So there are many works which looked into the detection, the parameter estimation, the astrophysics, the test of GR aspect, and so on, by combining the information from the two bands, that is LISA and C. So now we're looking at some of the results. So this is a result from Enrico's paper in 2016, where they argued that so the dipole radiation again is something which is like was pointed out, is very badly not badly estimated. It's the best, but it's no longer not compatible with the binary pulsar test. But because it's a low frequency information based post-Newtonian coefficient, they argued that by combining the LISA with 3G detectors, so what is shown on the left panel is the advanced LIGO bound, existing advanced LIGO bound. So I think that is improved later on, but that is somewhere here, right? And now they consider various LISA configurations. As I said at that point, the LISA configurations was not finalized, and for various types of sources. And they argued that by doing multibanding, you can get to extremely good bounds. If advanced LIGO was there, which could be even more with the CE detectors, the bounds could be as good as 10 raised to minus 8, can get to 10 raised to minus 8. That is where you can get to if you are able to combine information. So this basically means that combining the information does help you get improved bounds because of the mutual complementarity of the LISA band with that of the CE band. You are able to gain much more. And if you look further, this is another work in 2019 by Carson and Yagi, where they looked into the single band bounds, the single parameter again. So this all one parameter. So they studied how the one parameter test would improve with multibanding. They considered many detector configurations. So something TAN-Quin is something like a LISA detector, I think Chinese, proposed by China. And Desigo is something which happens to be in between LISA and LIGO bands. For example, something between 0.1 to 100 hertz or something. So that's again a bit somewhat futuristic. But again, they did an extensive study of how much things will improve. So the bottom panel shows the improvement factor in some sense for different types of detector configurations, and you can see that the factor of improvement could be of the order of 40, 50, and so on for some of the PN coefficients. So that indeed means that even one parameter test would definitely benefit from multibanding. Now, that was the context in which we approached the problem. We asked the question that given the complementarity of the LISA and CE bands, we wanted to ask the question, can you do the multi-parameter test using multibanding? And the answer seemed to be yes in the following sense. So what we did is the following. So we considered the GWTC1, which is the O1, O2 binary black hole properties, how they are distributed, mass distribution, spin distribution, etc. And we did a simulation, and we asked how many, if this population of binary black holes is the underlying the true one. How many of these systems will have multi-band counterpart? How many of them will be detected in both bands? We found in a year, somewhat like 100 events is what we found will be detected. And then we asked the question that if you take 1 year of LISA observation, 1 year of CE observation done by detector, and if you go back to the LISA band and integrate the LISA data for 5 years, and how well we can do, right? And so we did not only that, so we are got around 90 or 100 events, and we combine the information from each one of them. So this is a result after combining the 100 odd events for all of them about the multi-parameter test, and you can look into the most striking thing is the 8-parameter thing that is here. So it seems that all the 8 parameters can be estimated to a value of the order of 10 raised to -1, which of course, just these 3 goes to out of 10 raised to -1. All other things are in the order of 1%. But even then, this is much better than what anything else can do. And with depending upon how the rates improve and how the properties of the bunny black hole population improve, this process can be even more effective. And what is also shown, if you don't want to do the 8-parameter test, we can also do the 7-parameter test. We just take only the first 7 parameters. You can see that they can be done to very extremely good accuracies of the order of a few percent. So this seems that the multi-banding can provide a way of carrying out this multi-parameter test, which is extremely demanding, but it's of course of fundamental importance if you want to map, if you want to rule out theory. For example, in future, if you want to say that, okay, I detected something, I find a deviation at 2 pn. That is something I want to. Can I rule that theory out? Right? If you did 1-parameter test, you may get a bound that is too good, but they may not be be close to the reality. So you may want to use the bounds which are more conservative, which will come from the multi-parameter test, and then apply them. That's a more fair way of dealing with the thing. Of course, there may be situations where you may be okay to do a 1-parameter test also, but that may come with more assumptions about the sources or the about the additional fields you are invoking or interactions you are invoking and so on. So, but so the basic message is that to do the multi-parameter test, multi-banding seems to be the way forward. Okay, so now how does the multi-banding help? So this is a plot. I mean, this just we can go to the plot. This for just to summarize, the Lisa and C bands are complementary. So when you basically what you do is when you add up the Fisher matrices for Lisa and C, when you add them, you get a lot of cancellation of the correlations there, and hence your sum of the two, that is what you would invert to get the errors on the multiband thing, is much better. So there are cancellations of the correlations due to this addition, which is due to the complementarity of Lisa and C, and that is what really helps us to really push the multi-parameter test to accuracy of the order of 0.1. Okay, so I think that's pretty much what I wanted to speak. So just to summarize, I have argued that this parameterized test is a very useful theory agnostic method to probe deviations from GR, and the existing limits are consistent with GR, but yield very interesting bounds on some of the deviations. And the multi-parameter test will play a very important role in the future, especially if you want to rule alternatives to GR out. And in between, like I argued, the singular value decomposition of the PN coefficients may offer an interesting alternative, at least with the kind of sensitivity that we have got. Though it cannot, it cannot be used, the bound cannot be used to rule out theories, but it may be a very interesting way of optimizing the null test of GR. And again, the important thing to take home will be that the multi-banding, where you observe Lisa and C, will have a tremendous impact on all tests of GR, almost all tests of GR in the future, and will have, and it's going to play a very important role again in a decade or so. Okay, with that, I think I'll stop, and we can now talk about any questions or anything else you want. Thank you so much.
Yeah, thank you very much. So, Arun, there is one question from Sanjeev Kalita.
Okay.
So the question is, how far are we to test no-hair theorem, or to know if modified gravity satisfies no-hair theorem? And what about scalar hairs?
Yeah, so I think some of the, at least last two questions will be maybe addressed by Peter Cardoso's talk or so on later. I did not talk about it much. But again, regarding the no-hair test, I don't know whether you are referring to the ring down test. I did not talk anything about the ring down or the quasi-normal mode, but they still are interesting things. So, but you require a system that is high mass, like 200, 250 mass and so on, that can give you a good bound on the ring down structure, but which we have not seen so far. But the other way of bounding the ring down is what I think Sumanta was asking, is about talking about the no-hair aspect of the component black holes or component objects. Right? So that can still be done either by measuring the spin-induced multiple moment or the tidal deformability or tidal heating. That again is an issue I think will come in Sukanta's talk and so on. So I think we are in good position in terms of answering all your questions. Though the accuracy will be shown in the coming talks. That may be a short answer.
Hi Arun, I have one quick question.
Yeah.
Two actually. So first of all, if the effects of parameters are not taken into the waveform, so how is the Chamberlain UNIS paper? They are trying to list all those things that they have checked. So first is that. And second, so
and
how
maybe
far
I can answer that first, if not I'll forget. So I think your question is that if we are not using a waveform which explicitly carries these free parameters in the analysis, how are we constraining them? Is that what you're
yes.
So I think that what they do is that suppose we take I hope you can see the screen. Suppose we take for example the dipole radiation. There's a beta parameter, right? So the beta parameter in GR is 0, and we obtain some bound on beta. So we say beta should be less than or equal to minus 10 is to minus 10. Right now, so this is a bound that is coming from the data, and now this value of beta should be respected by the formalism. So if the theory requires beta to be like higher than this, then you can rule that theory out, because we have seen that there is no beta is 0 up to this accuracy. So this is by translating these bounds on the Pn coefficients to those the theoretically required values of those formalism that we are ruling out or ruling in or constraining those class of theories. But there is no ruling out so far. I'm just saying that is how one would constrain, even if we did not have an explicit waveform that carries it.
Okay. So second question is, how far can I say that this is a test of the Pn formalism rather than a test of the GR itself? I mean, you are basically testing Pn, not GR.
Yeah, correct. So I think what you're saying is that we are indeed testing GR in the adiabatic regime or until just before the merger. And by GR, I mean, you mean the full nonlinear GR very close to the merger. Right? That's what you're
right.
That is true. So, but no, I'm saying we can do the test. So this test is largely facilitated by the fact that many other theories of gravity also have at least in the perturbative regime, they have got predictions, which is what we are using. But if you go to the strong field dynamics regime, there are very few theories of gravity for which we have done numerical simulations, for example, and so on. So there are many complications from the theoretical side if you want to do that. But we have done that also, which I did not mention. So what we can do in principle is that suppose we take the in-spiral merger ring down waveform, right? Okay, I can, since anyway discussion thing, I'll try to see if I can dig out the paper. It's okay. So I think what we do is the following. So we, just like how we parameterize the in-spiral, we can also do a parameterization of the merger also, because when you look into the phenomenological waveform families, they are analytical because they contain many information, all information to the numerical relativity. And these analytical things come with free parameters which are fitted with NR simulations to obtain the value. So in principle, if you deform those parameters, the merger related parameters coming from numerical relativity, and ask whether that is consistent with GR, that is of course a way of going beyond that. Now, of course, it's a bit tricky. I'm not a big fan of deforming phenomenological parameters in a regime where they have been obtained by calibration in the first place, and so on. So I think so we can do those tests, and they should be understood or digested with it's all the caveats that are given. But the other type of test, if you really want to test whether so you want to understand whether something really happened during the process of the merger, right? That will be answered maybe in Ajit's talk tomorrow. So there are very interesting tests which you can do between the what is predicted from in spiral and what is predicted from the mergering down. So the consistency between these two can be put to test to very good accuracy, and that to me is the most convincing strong field test in terms of the merger is included. So I think in the talk, Ajit will talk about some of them tomorrow.
Okay.
But this is so this. You guessed it right, but I'm saying you need to go beyond this to do this, which comes with its own caveats.
Right. Thank you.
Yeah. Any other question?
Can I ask?
Hello.
Yeah.
Hello. Thank you for very interesting report. Talk about such interesting theme. I would like to ask you about the large extra-dimensional theory. Is it the theory of type Arcani-Hammett, Dimopoulos Bali, or Randall-Sundrum, or it is some another extra-dimensional theory? It is the one question. And then the second, if it will be possible to discover some deviation from general relativity, would it said about the deviation from standard model for particle physics?
Yeah. Okay. I think I don't know the answer. I don't know the answer to both the questions actually. So I don't know what kind of. So you're asking whether that is the Randall syndrome type extra dimension or not. What they use in the -4 PN. So if I don't know. I think I had to look into this paper to see what kind of modification they are talking. But if I remember, I think Randall syndrome type thing give a 2 PN type modifications, and maybe it is some other thing. But again, I am not an expert and I don't remember. Now coming back to the question about what test, if you see a deviation from GR, what that would imply for the standard model. I mean, I don't know whether the standard model does not include gravity, right? But of course, in the grand scheme of things, if there is a deviation from GR, many of the physics you have been using will have to be re-examined. And if that comes, if the deviation comes from some quantum gravity, if you detect some deviation coming from some quantum gravity inspired models, and you're sure about that, let's say in a kind of situation, in those situations, I think those fields may also affect the standard model. But this is my guess. I'm not an expert in either of these.
Standard model does not include gravity. It's so real, but there are too many theories which include gravitational theory, so which predicts the deviation from standard model. So I asked this question.
Yeah, I think so. It could. I think so. It will depend upon what type of modifications comes in what details will decide. But it can have, in principle, of course, if you see a deviation from GR, it's going to be a big deal anyway for almost everything that we know. So I think it can have implications, though I cannot quantify the details.
Okay, thank you.
Yeah, thank you.
Professor Ghanasham Date has a question.
Yeah. Hello, Arun. Yeah, this question keeps coming again and again in these talks. Let me consider two waveforms, say F1 and F2, which depend upon two parameters, alpha and beta.
Yeah.
Alpha and beta may relate to example for parameters of the binaries.
Yeah.
Now, one of the form is a GR form, other is some other theory.
Yeah.
Both forms are very similar to each other, so they cannot be obviously ruled out or rejected.
Yeah.
Now, if I infer the two parameters, alpha and beta, by fitting the same data, I will get different values in general.
Yeah.
How do I know which one is to be chosen over the other? Because one is GR, other is non-GR. How do I discriminate between the two?
No, I think so. The thing what we do is that when we do what we do as of now, what we're doing is the following. So we have a data. We do a GR parameter estimation first. That's what we do. Then as a next step, we are looking for deviations from GR. And now, suppose I did analysis and in the second analysis where I introduced free parameters, and I see that there is a statistically significant offset in one of the free parameters that I introduced.
Oh, so these three parameters are introduced additionally, is it?
Exactly. So I think they are estimated together with the masses and all the GR parameters, these additional parameters, correct?
Yeah. Now, if I were to put the additional parameters and re-estimate the masses and other binary parameters, they will be different.
Yeah, so I think
so how do I know that I have not chosen the wrong theory?
No, I think they will be, so of course the error bars on the thing will anyway change. So there can be offsets due to this, but not major, no, we are not seeing very major offset. They're all lying within the statistical error bar. And if you see something which is, suppose suppose I featured a parameter and I found that, okay, that parameter is peaking at 0, that is fine. But my mass is now outside the 90% credible interval, my M1, M2. Then of course, I think I know that something is going on, and I think I will have to look into that. But all the things so far, we have found that even there have been some offsets, but those offsets are not unexpected given the extra thing we are fitting. And only when they go, when these offsets become very significant statistically, we have to look into this problem. At that point, we, like you said, we have to look into this problem more carefully.
Yeah, because the two forms could be, one of them is a 2PN form and other is a 3PN form.
No, that I didn't understand. I thought you're looking into...
assuming only the same parameters. I mean, I don't include effects of spin and so on. So let's keep those things simple.
Yeah.
Then again, my answers will be different, right?
So you're talking about simultaneous estimation of two of the PN parameters.
Yeah, for example. No, my basic problem is I have a waveform, a theoretical waveform, which depends upon some parameters to be estimated. Some parameters are related to the object that I'm studying, namely binary system. Which parameters are known, at least theory tells me there should be 3 or 4 parameters I want to fix.
Yeah.
My theoretical form that I choose, depending on which theory I have, may have additional parameters. That's a different story.
Yeah.
So the first set of parameters which are related to the binaries, those have to be estimated somehow. And then against that, I can compare the other parameters to distinguish between different theories.
No, so I think we do. So I think you're talking about. So there are two hypotheses here. One is a GR hypothesis. Second hypothesis is a non-GR hypothesis. Let's say, right? Yes. Now, I want to quantify the odds that GR is correct versus the non-GR is correct, or vice versa, as is coming from the data. And the base factors which we compute are all after marginalizing over all the parameters, and hence this ratio will include all properties of the posterior distribution. So
right. So if there are within the theoretical forms, if there are certain ratios which are different from which differ for different theories, but those are multiplying the parameters of the binary, then at least I can choose one form to fix the parameters of the binary and look at the consistency of the ratios of the coefficients.
Yeah.
Is that what is done? Maybe we can do it in the discussion session.
We can talk over email. I think that's
no, our discussion session in the afternoon.
Yeah.
In the afternoon, maybe it would be a better place to.
Right.
Yeah, sure.
Okay.
Thank you. Any other question from the audience? Okay. Yeah. If there are no other questions, Arun, I have just one small question.
Yeah.
Can you go back to the multi-banding, multi-parameter slide that you had shown?
Yeah.
Yeah, I think 31.
Yeah.
Yeah. So here, if I see the plot, then when you have a one parameter, the bound is much stronger than when I have 8 parameters, say.
Yes, correct.
Why is this? I mean,
yeah, I think that is what I was, was saying initially. So when you have one parameter, you got GR like 7 parameter, and one parameter, you are estimating only 8 parameters. Now, when you have the 8 parameters thing, you got 7 parameters from GR and 8 parameters from non-GR. You're estimating 15 parameters. So you are estimating many more parameters, and hence the bounds are weaker.
I see. So that means if you do multi-parameter analysis, the current bounds are supposed to be more relaxed, or?
No, so when you do the multi-parameter thing, it's going to be much less stringent. The multi-parameter thing will be less stringent than the one parameter one.
I see.
So it's going to, so that's going to go up. But the point is that these are more closer to a possible deviation when you are trying to map it onto the reality is what the argument is, though it's weaker.
I see. Okay. 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 Thank you, Arun.
Yeah.
And, yeah. Any other question from the audience? Okay. And if there are no questions now, you can ask questions to Arun during the discussion session, and I mean, he will be happy to answer. So the next talk will be by Professor Shukanto Bose from 2 p.m. So, I mean, we can just have some lunch, which is not possible virtually. And then we'll come back again at 2 p.m. with Sukanto's discussion. Okay, so see you all at 2 p.m.